Welcome to part 2 of processing your data for the Momentum Lab. To sort of recap what we've done so far and what we're going to do, the focus of these videos is on these calculated values for the lab, where you were supposed to find, and we did in the previous video, your weight and mass based on this part of the data. What we're now going to look at is how you calculate the impulse applied by the net force. The other stuff, like speed on leaving the platform, is very straightforward, but the impulse applied by the net force is something that you're going to have to calculate using Excel and what's called the trapezoidal method. Because without Excel or Sheets and the trapezoidal method, there's not really a good way to say find the area underneath that curve. All right, now what is the trapezoidal method? Well, you should recall from previous material in the course that if you find the area underneath a graph, it usually represents something. Specifically, it's the integral, but what exactly that integral is depends on exactly what the graph that you're dealing with is. In our case, we're talking about a force versus time graph. And the area under a force versus time graph is going to be the impulse applied during, say, a collision or explosion or whatever it may happen to be. It's the impulse. Now, if you have some nice, easy shape, like you always have in the textbook questions, well, then you can just be like, oh, area of a triangle, area of a rectangle, I got it, add it all up. But if it's some curve, then maybe it's not going to be quite so straightforward. If it's a curve, ideally, you would have a function for it and you would just do calculus. But if it's a really messy shape, then the only way to really do it is by breaking it up into different shapes. All right, and the one method anyway that is used is the trapezoidal method. So that's where you use the formula for the area of a trapezoid, okay, and then from that calculate the area. So this is, well, technically a triangle, but whatever. I guess it's a trapezoid, sort of trapezoid. You'll notice all of these have the same width. They're all broken up into 1 second widths. Fine. We could have done this differently, right? They could have broken it up into half-second trapezoids, but that would have been more trapezoids and perhaps therefore more time-consuming to calculate. Okay, so the width, though, you'll notice is always one value. Each of these trapezoids is the same width. However, the height 1 and height 2 values are going to be different for all of them. This first trapezoid has a height of 0 to start with, and a height of, looks like about 5.2 or something like that, or, a little more than 5. Okay, so whatever, we could plug in those numbers in here, and that would give us the area of this trapezoid. For the second trapezoid, same width, right, but different heights. And again, we could plug them into the formula, calculate the area of this trapezoid. If that's how integration worked, meaning if that's how you were expected to do every integral, integration would be horrible and time-consuming. Because you'd have, doing this by hand gets to be a miserable task, right? You got to use this formula, in this case, 6 times. But if we broke it up into skinnier and therefore better trapezoids, we would have to do the calculation 12 times, which is not something that I really care to do. So instead of doing it manually with our many thousands of data points, what we are going to do is make Excel do the area of a trapezoid. So in the previous video, you probably saw a little bit of the wonder of Excel, which is that you can make Excel calculate things for you. I'm going to do the jump here just for demonstration, okay? I'm going to use this area of a trapezoid formula when I'm calculating the area under this curve right here. Now, the values I'm going to be using for my width are based on my time axis. The values that I'm going to be using for the H1 and H2 are going to be based on my net force axis. So this column right here. All right. So here we go. We're going to type in the formula for the area of a trapezoid. So equals, all right, well, actually, we need to start down here. We can't do it for the first row because there's nothing above it. You'll see why in a minute. We need to have two values for everything to subtract. All right, so here we go. Equals. All right, now I have the width is based on the change in time here. So equals, for my width, we're going to do parentheses, this one minus this one, close parentheses. Now, for me, that's going to be 0.001 every single time because I set my force sensor to measure at 1,000 hertz. You probably set yours to run at 500 hertz. But if you'd set it at whatever value, right, the width is going to be some constant value based on the number of hertz that you chose. So I could, in theory, just type in a number here, but to make it more universal, I'm going to go ahead and say we'll do this one minus that one, and that will be the width every single time. All right, so width is change in time. Okay, and then times, let's see, it says h1 plus h2. All right, h1 is going to be my net force, and then the net force from the row above. This is why I didn't start at the top one right here, because I would have to then put in another row up here, and I'd have to make up numbers. So I have to start one line down. Okay, and then I close my parentheses, and because the formula said so, divide by 2. Okay, and that is the area underneath our first trapezoid, which is a small area. It's fine. Because the net force at this moment is very small. Mr. Erica, why does this look like it's at like 755? Because remember, this graph was the graph of force versus time. If I made a graph of net force versus time, that's probably more useful for me to look at here. It will look like that. Oh, it's out of the way. Okay, and so what I found right here, this number, is the area underneath just this first teeny tiny little trapezoidal point down here that I can't even zoom in on. It's the impulse applied during the first 1/1000th of a second. Now, if I want to know the impulse applied over this entire time interval, I will now do the following things. I don't know what step I'm on, but step next is we drag this formula. Whoa, and stop there. Each of these numbers represents the impulse applied over 1/1000th of a second by the net force acting on me during my jump. Now, if I want to know what the total impulse was, it's just the sum of all of those things. So I'm going, ooh, it even suggests, that was very helpful. Good job. It says sum this stuff. So if it didn't make this suggestion, I could always type that in. That's what I'm going to do just because I hate taking Google suggestions. I will say equals sum of this one, right? I click on it. I scroll up to the top. I select my top number, close parentheses, and hit enter. And looks like the total impulse acting on me during my jump was 242.6. Okay, so this is the jump impulse. Awesome. All right, I can now repeat this exact process for the landing. Now, I don't actually need to retype the formula in all over again. I could select this, right? All right, go up here to the top and select the text, copy it, go down, do the landing, and as long as everything's pasting in the exact same spots, it should work just fine. All right, if it doesn't work out, we can always retype the formula. It's not a big deal. And then I can take this and drag it down. Okay. All right. And then equals sum. I'll go ahead and take their suggestion this time. Enter. 230.7. All right, and that is the landing impulse. All right. So that's how you find the area under your graphs, right? For the jump, right, the impulse area under this graph was, scroll down, was 242. And during the landing, I had 231, basically. You should realize that the impulse should be identical for the two graphs. And it's not exactly identical. It's not that far off, right? 231-ish and 242 aren't that different, but they're not exactly identical. All right, and thus, later on in the lab, you'll end up calculating a percent error and such. All right, now, going back to what it says here. We have now done 2 and 3. Step 4, speed on leaving the platform. All right, speed on leaving the platform is going to be based on the idea of delta P, your impulse, equals mass times delta V. Let's go back to my weight over here. In this tab, I calculated that my mass was 76.94, let's call it, all right? If I want to know, therefore, the change in my velocity, I will say equals impulse divided by 76.94. I think that's what I said. Yes, it was. Okay. And I have then that my impulse is, or my change in velocity is 3.15-ish meters per second. That is reasonable. If you're a average human of my build, you can probably jump at about 3 meters per second. Not impressive compared to, say, like a flea or a kangaroo. That's probably just an average normal person. All right, now, what if you're an above average person? 5 is, I suppose, possible, but very unlikely, okay? If you can jump at 5 meters per second, that means that your feet would end up about 4 feet above the ground, right? That's probably not actually reasonable. I'm guessing most people cannot jump 4 feet in the air, okay? And believe it or not, that's how high 5 meters per second would take you. So, but this is probably pretty reasonable. All right, now, last couple of things. Maximum height, you should be able to do this based on conservation of energy. I will leave you to figure out how to do that, since that's something we've talked about in class before. But if you know that this right here is your jump speed, right, the speed with which you are leaving the platform, then you should be able to use conservation of energy or 1D kinematics to figure out how high you go. All right, last thing, percent difference. The percent difference formula can be found in your lab handout. In case you've forgotten, though, I will refresh your memory. It should involve subtracting those two values and then dividing by the average of them. Multiply by 100, and now that is a percent difference between those two values. Ideally, your percent difference is 0. In this case, you can see it wasn't, but our results really overall were not that bad. All right, I hope this helps. Let me know if you've got any other questions about how to execute the lab, and I will do my best to steer you in the right direction. Thanks.